Now that we know that any LTI system can be defined by a constant coefficient differential equation, now it is time for us to look at how we can solve this equation and actually get to know about the response of the system using this differential equation. So from the first part of our lecture, we are sure that any LTI system will have a defining constant coefficient differential equation, which will have a general form of this. So the solution of this differential equation will give us how the system behaves in case of any input is given to it. So if we solve this differential equation, we will eventually find out the YT, which is actually the response of the LTI system. Look here, the response of the system can be divided into two parts, or it is a summation of two different parts. One is the homogeneous response or homogeneous solution, another one is particular solution or particular response. So now let us go one by one. We will first look at the homogeneous solution. So the total response of the LTI system has two parts. One is homogeneous part and another one is particular part. So first we will focus on the homogeneous solution. Homogeneous solution is that solution of the differential equation that we derive is that when we consider the input is zero. In this equation, look here, there both the parts are available. The output parts are available and the input variables are also available. If we consider the input is zero, that means if we consider this whole part is zero, then we will obviously have one differential equation and that equation can be solved, and that solution is called homogeneous solution. There are other names of this homogeneous solution, that is zero input response. As we have already mentioned that while solving this homogeneous solution, we will consider that the system has zero input given to it. And this response is also called natural response. What about the other response? What is this particular solution? The particular solution is for the solution of this differential equation when we have some input given to the system. So for any given input xt at t equals to t greater than 0, there will be some response available at the system's output. That output is that output can be calculated if we calculate this particular solution. This solution is also known as zero state response and also forced response. So our focus is on, first we will get to see how the homogeneous solution is calculated. So as we have already discussed, this is the natural version of the constant coefficient differential equation. And for homogeneous solution, just like Hanov's can snap and get some part of the equation removed, we will remove this input part and replace it by 0. So then we will have another version of the differential equation. And if we solve this differential equation now, the solution will give us the homogeneous solution. So how can we solve this type of equation? I think you already have some idea from your mathematics course, but let us take you through the process again. If we are given a differential equation where we only have the uh, derivative of y's or the outputs and the input is considered as 0, in that case, we will consider a solution. One solution will be assumed. That is in the format of c e to the power lambda t. So here c is a constant. You can consider it like any variable, and lambda is also a variable, so you can consider this lambda to be any other variable as well. For example, you can consider it k e to the power mt. There is no harm to it, but for the time being we will consider this is the assumed solution. And if we have assumed the solution yt as this, and at the left part of the differential equation you can see that there are multiple derivative operators, so we have to replace these operators by this solution. So in place of yt, we will put c e to the power lambda t. In place of dy dt, we will put the constant first, then c lambda e to the power lambda t. In this way, and we will have to go on and on. uh, up to the level of derivative we have. Then we will eventually get a characteristic polynomial that would look like this. And then from here, we will be able to find some solution of these polynomials. And then using the solution, we can plug it into our assumed solution and we can have a format of the solution for homogeneous part or the homogeneous part solution or the zero input replacement. So for our case, we have assumed this differential equation, and for RLC case, so let us solve this RLC case. And as we have discussed for the homogeneous solution, we will look at how the homogeneous solution will look like. Let's assume the value of the capacitor for this particular RLC circuit is 10 ohm. Value of inductance is 2 Henry. And value of capacitance is 0.125 farad. So using these values, we can replace the values of constants first. So eventually, this equation will turn into R by L will be 5 given dt, and plus 1 by LC will give us what will 2 into 1.25, multiplying this 2 will give you 0.25, and if we flip it, it will give us 4. And 1 by L is 0.5 dx dt. So for homogeneous solution, we will have to assume this part to be 0. So let us assume this part to be 0. So what we are left with? We are left with double derivative of y plus 5 into single derivative of y plus 4 yt. So we will assume a solution yt to be c e to the power lambda t. If yt is c e to the power lambda t, then first derivative of yt will be c lambda e to the power lambda t, right? And what will be this double derivative? As we have seen the steps, we now have enough values in our hand to replace the original equation by the assumed solution. If we replace these values here by the assumed solution, we will eventually get c lambda squared e to the power lambda t plus 5 c lambda e to the power lambda t plus 4 c e to the power lambda t is equals to 0. From here, we can take common c e to the power lambda t, and we will be left with lambda square plus 5 lambda plus 4, which is equals to 0. As this is a non-zero quantity, we can uh, take it to the right hand side and consider the whole situation lambda square plus 5 lambda plus 4 to be 0. Now we are here with the polynomial, characteristic polynomial. So solving this equation will give us some values of lambda. So how we can solve it? Lambda square plus 4 lambda plus 4 equals to 0. We do lambda here, lambda plus 4 plus 1, common lambda plus 4 equals to 0. So this polynomial gives us lambda plus 4 into lambda plus 1 equals to 0, which is the value of lambda here is minus 1 or minus 4. So what does it mean? The characteristic polynomial is giving us the value of lambda to be minus 1 and minus 4. And the assumed solution that we started with is c e to the power lambda t. So for this case, the homogeneous solution will be c1 e to the power minus t plus c2 e to the power minus 4t. Okay. How we have come to this point? There are some rules. So the basic thing is that we have to replace our derivatives by the assumed by the versions of assumed solution, and then we will come to this point that we will have a characteristic polynomial, and after solving the characteristic polynomial, we will have some solution for this lambda, and by observing the nature of the lambda, we can say that our homogeneous solution should look like this. Where we will find this? In the next slide, we will see what to do for different cases of solution that we get from lambda. For distinct real root, if we find distinct real root, just we have found right, right a few moments ago that the value of lambda came to be -1, -4. If we find these distinct roots, then the homogeneous solution will be of this order, right? In the previous case, we have said that our homogeneous solution for the RLC circuit case was C1 e to the power minus t plus C2 e to the power minus 4t. That isn't the final solution. We have to find out the values of C1 and C2 by observing the initial conditions that will be given in our maths. For that particular problem that we have solved a few moments ago, there were no initial condition given, but we will see, we will work out some examples where there will be given some initial conditions will be given. So from that, we can calculate the values of C1 and C2, and that will give us a complete homogeneous solution. Okay. What happens if we have repeated real roots? For example, we calculated lambda and it appeared that the solution came out 442. So what will we consider the homogeneous solution then? In that case, the homogeneous solution would be, according to this formula, C1 plus C2t e to the power lambda 1t, or here the lambda 1 is 4 actually, e to the power 4t plus C3 e to the power 2t. If we have repeated roots, for if there were 4 repeated roots, let's say 3 repeated root and 4, in that case the solution would be C1 plus C2t plus C3t squared e to the power the common root here was 4t, then plus C4 e to the power 2t. So in this way the solution will be, and that will not be the complete solution. We will still have to find out the value of C1, C2, C3 and C4. If we get some complex roots, like if the solution of lambda comes out to be alpha plus minus j beta. So what will we do then? In that case, the homogeneous solution will be like this. So if we have this alpha beta, in case of alpha beta, let us write 2 plus minus j3. So in that case, our homogeneous solution will be e to the power 3t, sorry, e to the power 2t c1 cos 3t plus j c2 sin 3t. So this is 2, and it can appear that the value of lambda came out 2 plus minus j3 and 4. So what will be the homogeneous solution then? In that case, the homogeneous solution would be e to the power 2t c1 cos 3t plus j c2 sin 3t plus c3 e to the power e to the power 4t. So this is how the cases will be. So for the characteristic polynomial, only three cases can happen. We can have distinct roots, we can have some repeated roots, and we can have complex roots. So for these three cases, we have covered how the homogeneous solution should look like. So that was the whole procedure of considering the homogeneous solution or zero input response of the differential equation for a given LTI system. And what about the particular solutions? While calculating the particular solutions, we have to consider the input given to the system. So whatever the input is given to the system, for that case, we can consider the a particular assumed particular solution that would be kxt. Look here, there is a table given. If the input is a, in that case, we have to consider the kxt. So if you multiply k with a, it will eventually be a constant. So in that case, the assumed particular solution should be k. If we have a step input given to the system, the assumed particular solution would be k step input. If this is the one exponential is given to the system, so the our assumed particular solution will be k into the exponential. In this way, whatever the input is given to the system, we have to consider one particular solution that is going to be k multiplied the x. That is the general procedure. And we will look one example where we will have to work out both the homogeneous solution and particular solution. So that was the basic idea. If we are given a differential equation to which represents an LTI system, and how to look at the solution or the response of the system from the given differential equation. So, if I summarize, the total response conclude total response has two parts. One is homogeneous solution part, which is also known as natural response or zero input response, and we have another part that is called particular solution, which can be known as zero state response, and also which is known as forced response. So the both responses uh, combinedly make the total response of the LTI system. And we have seen in this video how can we go about to solve the homogeneous solution part, and some techniques that we have to apply to come to a conclusion when we want to calculate the particular solution. In the next videos, we will see a full-fledged example uh, for a differential equation given. How can we solve the total response of the differential equation?